It's our pleasure to have our Fermilab speaker of the semester. We have Kevin Kelly. So he's starting his PhD at Northwestern. He has published over 20 papers, mostly on neutrino physics and covering various aspects of the physical field. And today he's going to tell us about the new detector at DUNE.
Hi, thanks for the invitation. It's a whirlwind trip to come down here, but I am really happy to be here. Like Mo said, I'm going to tell you about the DUNE ear detector and some ways that we can use it in an orthogonal direction to neutrino physics. For some interesting stuff. So I'll give some background theoretical motivation for why we think what we're doing is interesting, and then I'll talk about DUNE not as a neutrino experiment, but as a Meson experiment. I'll give some overview for the ear detector complex at a very, very high level, and then I'll talk about some ongoing work that should be out next week about searches for new particle decays in the ear detector complex. And if time permits, I'll talk about new physics in particle scattering in the ear detector. So to give a one-slide summary of why we think what we're doing is important, actually 2 slides, there is an abundance of experimental evidence, observational evidence for dark matter in the cosmos on very, very large and very, very small scales, from the bullet cluster to the CMB to the rotational curves of individual galaxies. But from a particle physics perspective, from the way I think of things, there's no clear answer to explain what we see. Now, for the past 30, 40 years, I would say that the standard bearer for a particle physics explanation of dark matter has been the WIMP. The WIMP is nice because it is predictive. If you assume that the dark matter was in thermal equilibrium with the standard model, and then at some point when the temperature of the universe cooled enough such that the interactions of that WIMP freeze out, it will freeze out at the abundance that we see today if it has a weak scale mass and if its coupling to the standard model is similar to the weak interactions that we see in the standard model. Nice because it's predictive. However, people have, there's a whole industry looking for WIMPs, and unless you believe gamma, like you were talking about at lunch, there's no clear answer in this parameter space. We don't really have a reason to believe in WIMP dark matter. Now, we're getting better at looking for it. We're setting limits every year, even smaller cross sections, starting to get closer and closer to this neutrino floor. And that means that people are going to have to start innovating on how to get below this. It's definitely a direction that's worthy of pursuing, but I like to think, what other directions can we go? So if we're going to abandon the WIMP paradigm or start looking in different directions, we should be interested in either heavier or lighter dark matter. If dark matter is lighter than this GeV to hundreds of GeV range, then you can still have this same thermal freeze-out mechanism. However, in order to set the correct relative abundance, you need additional mediators, additional light mediators to do the trick. Now, from a theoretical perspective, you can ask, okay, add some new mediator, call it a vector, call it a scalar, and say that it connects this dark matter to the standard model. Well, how should it interact with the standard model? You can write down a Lagrangian and come up with a million different ways to do this, but we think that using renormalizability as a guiding principle is a good way to go. And so if you use renormalizability, there's only a handful of operators you can write down to tie dark matter to the standard model. There's a scalar portal, so this is the standard model pigs with some new scalar. There's a vector portal where you have the standard model hypercharged field strength tensor coupling to a new field strength tensor. You could have some anomaly-free current of standard model particles coupling to a new vector. Or you could have the neutrino portal, where this is the standard model lepton doublet and the Higgs coupling to a new fermion. So from this point of view, there's only a finite list of options to tie dark matter to this. Now, forget everything I said about dark matter in the last 5 minutes, because now I'm just going to focus on these mediators. So these mediators aren't going to be the dark matter, but they could be something relating the standard model to the dark matter. And these are the kinds of particles that we think we can search for in DUNE. So DUNE, the Deep Underground Neutrino Experiment, is expected to come online in the next decade or so. A powerful neutrino beam originating at Fermilab, going to South Dakota. It is, as this says, the next generation neutrino facility, but it is also the next generation meson facility. Now, of all of those normalizable operators that I wrote down, they share one important thing in common, and it's that if you believe that that is the answer, then you should be able to produce these mediators in meson decays, depending on what their mass is. So depending on their mass, they can be produced on shell in the decays of mesons, which we produce in the DUNE facility. Now DUNE will have a 120 GeV proton beam hitting a graphite target, and that produces a bevy of both neutral and charged mesons. So this is a theorist's depiction of what that looks like. I'm pretty sure this is accurate. There is this blue thing that is carbon. There are these red things that are magnetic focusing horns. And out of the target come things like neutral pions, neutral etas, charged pions, etc. And depending on how you're operating the magnetic focusing horns, you either select positively charged mesons or negatively charged mesons to go in the beam direction and try to divert the opposite charge away. Now, of course, that won't affect the neutral mesons, and it also won't affect any mesons that decay too quickly to have their trajectory changed by this. So in terms of neutral mesons, the ones that we're interested in for this study are pi naughts, etas, and neutral kaons. Now we can use Pythia and ask it if we have 120 GeV protons hitting carbon, how many of these do we get out on average per proton hitting the target? And it's about a few pi naughts and a couple times 10 to the minus 1 for the slightly heavier mesons. Now, we want these to be the particles that decay into the new physics particle in probably some rare decay process. And that will require that these particles, these parent mesons, are pointing in the correct direction. The bulk of the flux, if it's pointed towards the near detector of DUNE, then its decay products will be preferentially in that direction as well. So we use Pythia to extract the 4 vectors of these particles after producing them in the target, and we keep track of their 4 momenta and ask questions like, are they pointing in the right direction? So we can plot some of that information. This is what I call kinematic boost, because you have 120 GeV protons, you have about 15 GeV of center of mass energy, so any products of that interaction will preferentially be forward going. So there are 4 different lines on this figure, and the point is that they look the same, each one indicating a different meson family. And what we are showing is the fraction of events that have a given, what we call PT over PZ, transverse momentum over forward-going momentum. And this is supposed to serve as a proxy for how forward-going are these mesons. So these are our neutral mesons, and we see that they tend to have PT over PZ on the order of 10 to the minus 2. You can also think of this as the tangent of the opening angle of the mesons relative to the beam direction.
Sorry to interrupt. Are you going to talk more about the properties of the near detector that you assume?
Yeah.
Okay.
So we want small PT so that they're in the correct direction because it's on axis in our assumptions. Now, this is for the neutral mesons, but what about the charged ones? So like I said before, the goal of DUNE isn't just to make a bunch of mesons, it's to make a neutrino beam. And they want to make a pure neutrino beam. They want to have just muon-type neutrinos in their beam, no anti-neutrinos. So to do that, you need to sign select your charged mesons. The neutrino flux comes from charged pion decay predominantly, and so you want to select pi pluses that give you mu pluses and mu mu's, and you want to divert pi minuses that would decay to mu minuses and anti-muon neutrinos. Now, of course, such an experiment isn't perfect at that. You want to get it as pure as possible. So I'll show how well they can do that. These are the same production quantities as I showed for the neutral mesons. about the same number of pi pluses and pi minuses as pi naughts, similar for charged kaons. And then we'll also care later about d mesons, and we see that we get a few times 10 to the minus 6 of those per POT. Now, DUNE will operate something like 10 to the 22 POT in its runtime, so we will still get a significant number of these. Now, Pythia on its own is not able to give us a simulation of something like the focusing horns. We have to rely on information from the DUNE collaboration to do that. And so there's a working group within the collaboration that can produce this kind of output and give us 4 vectors of charged pions and charged kaons after they have traveled through the focusing horns during either neutrino mode or anti-neutrino mode, so that we can diagnose these kinds of kinematics. So now, instead of plotting that PT over PZ, what this is where the parent mesons tend to decay because they are long-lived, as a function of how far downstream from the target they are. So there's a long tail because of the lifetime of these mesons. There's a sharp peak here because this is the end of the decay volume. A non-negligible fraction of pions and kaons will reach that rock and decay at rest. And we also see in this that the positively charged mesons, the pi pluses and the k pluses, decay further downstream, and the negatively charged ones decay further upstream because they're being diverted into the rock, the pipe, etc. So this is all during neutrino mode, and we see that it's doing what it's supposed to. We can also look at the same quantity, PT over PZ, that we did for the neutral mesons, but for the charged ones. So the gray line that's running through the middle here is the line that I showed for the pi naughts previously, that are not deflected by the focusing horns. And now I'm comparing that against the pi pluses, which we want to be focused in the beam direction, versus the pi minuses that we want to focus away. And we see that, like I said, lower PT over PZ is good. It's in the beam direction. Higher is good if you want that thing to be diverted. And that exact thing happens. The pi pluses tend to decay with smaller PT, and the pi minuses tend to decay with bigger PT. We can do the same exercise for the kaons, and here we're comparing the green and the purple. Again, the green tend to be pushed towards lower PT compared to the purple. Now you see that the separation isn't as good for kaons as it is for pions, and that's because that's not the point of DUNE. DUNE wants to separate the pions. If it can separate the kaons, that's a side benefit. Okay. Now to appease Louis, let's talk about the experiment. So there is a whole host of pieces of the DUNE ear detector complex. I'll talk about a subset of them. Now, the goal of DUNE is to measure oscillation physics. And the FAR detector, which is liquid argon, in order to constrain the flux at the near detector to do oscillation physics, it helps a lot to have the same target material at the near detector as you do the FAR detector. It allows you to reduce systematic uncertainties greatly. And so the main component of the near detector is a liquid argon near detector that will allow for percent level constraints on the neutrino flux to study FAR detector oscillations. So this is the liquid argon near detector. It is roughly 50 tons in fiducial mass, a few meters in each direction. Now there are a few caveats to this simplified picture of things. The first one is that compared to the FAR detector, 40 kiloton, tens of meters long, the near detector is small. And this means that if you produce charged particles in the liquid, many of them will leave the fiducial volume before stopping. And if you have a track that exits, you can't measure its energy perfectly. And so the solution to this is that immediately downstream of the liquid detector, they're going to put a gaseous argon time projection chamber. It's lower density, and it's inside a magnetic field. So this allows you to measure the momenta of particles that come from the liquid into the gas very precisely, and reconstruct the entire event a lot better. So it consists of a gas argon time projection chamber with a electromagnetic calorimeter surrounding it, all within a magnetic field. The other caveat about the near detector is that despite using the same target material at the near detector as the far detector, there are still a lot of uncertainties when it comes to neutrino cross-section scattering on high density, high Z targets, specifically argon. So the solution for this is to have a movable near detector. You may have seen this little conveyor belt in the previous slide. This is to allow the liquid and gas detectors to move off axis, something like 20 to 30 meters in the transverse direction during operation. The reason they want to do this is because if you are focusing your charged pions to get neutrinos in the beam direction on axis, then there will be some component of the flux off axis, but it will be lower, and it will be lower energy. So this is a figure of the neutrino flux at different on and off axis positions. The on axis distribution is broad, and it peaks at 2-ish GeV. But once you go 6 meters off axis, it peaks at 1.5 GeV, and the total flux, the integrated flux, is lower. As you go further off axis, it tends to peak at lower energies and have a smaller total flux. Now, how does this help this issue? Well, if you have a bunch of different measurements of your flux at different positions, then you can measure it more precisely at different energies and try to reduce these systematic uncertainties. This is the overall schematic of the near detector hull. In the transverse direction, here's the liquid argon detector, the gaseous argon, and then this is a simulator tracker that will stay on axis to measure the flux and monitor it. And then this is the concept of it moving roughly 30 meters off axis. And it can get up to a few degrees off axis. Yes?
Just out of curiosity, can you go back?
This one?
Yeah. So here, I guess, once you move the detector and the neutrino energy is peaking at in between 2 GeV, then I suppose I remember the resonance production.
Mm-hmm. Yeah, you kind of sweep through the resonance production.
Right. So then, do they plan to perform the in situ calibration? I mean, I think the resonance production cross-section is not well measured, right?
Mm-hmm. I assume they plan on doing that. When they talk about PRISM, what they talk about it for is to do a far detector oscillation analysis. And they do this linear combination of all these fluxes to predict an oscillated far detector flux. It's very black box, but they claim it works. Now, yes, you could just use this to measure cross-section as well, and probably do different selections for the resonant production and constrain those a lot better. If that's what you're interested in, I'm sure this would do the trick. Okay, so let's make this a dumb theorist's view again. The high pressure gas TPC inside the ECAL, inside the magnets, is known as the multi-purpose detector, or MPD, and that's what I'll be focusing on for the bulk of this talk. So schematically, there is the target that produces the mesons and the focusing horns. And there's about 200 meters of decay volume until you hit Earth. There's about 300 meters of Earth until you get to the near detector hull. And inside the near detector hull are the liquid argon and the multi-purpose detectors. So we'll be focusing on this for the bulk of the talk. So let's talk about decays of new physics particles.
Like one more quick, do you use atmospheric argon for this, or?
I don't know if it's
Just the one with a bit bigger backgrounds?
I don't know. I assume yes.
I would assume yes, but okay.
Just to get the volume. It's about a ton in mass, so it'd probably be difficult to get
That's what I
too much. Yeah. Okay, so this is zoomed in on that. So the question is, why do we care about decays, and why did I talk so much about this multi-purpose detector to care about decays? So if you're looking for new physics in a scattering process, then your signal and background rates will both scale like the mass of your detector. Now, in a neutrino environment, your backgrounds are going to be predominantly neutrino scattering. That produces a signal that could mimic whatever new physics signal you're looking for. So if you're looking for new physics here, your signal and background scale like the mass. They'll both be high, and they'll both be low here. your signal to background ratios will be roughly the same between the two. But on the contrary, if you're looking for a decay, then the signal will scale roughly like the detector volume, whereas backgrounds will still scale like mass. So in the liquid, you'll have some signal and some background, but in the gas, that signal to background ratio should be a factor of 50 higher. So whatever backgrounds you expect in the liquid should be a factor of 50 lower. You could measure those backgrounds in the liquid to predict what they are in the gas, for instance, and do a low background search for such processes. So the approach we're going to take here is we're going to assume that there's some new physics particle that in this slide I'll call X, why not, that can be produced in the decay of some parent meson P, and S is just some other standard model particle along for the ride. And if we fix the mass of X such that it's kinematically accessible in this decay, then we can simulate the decays of this parent meson using that Pythia or DUNE output. And we can keep track of the flux of X's that are pointing in the direction of the near detector hall. And we'll travel through the near detectors. And we'll keep track of their energies as well. And so if we have all that information, and if we know how X decays its partial widths into channels of interest, then we can determine how many decays will happen in some amount of runtime at DUNE. So this will be the general approach I'll take, and I'll go through a few different new physics scenarios, and we'll see what DUNE can do. So the first is dark photons, and specifically I mean that they're kinematically mixed with the standard model. So if we say that there's some new U1 that exists and it mixes with the hypercharged group, that's its field strength term, kinetic term. Here's its mixing with the standard model field strength tensor. Epsilon characterizes the strength of the mixing, and it has some mass ma prime. Now this is a common Lagrangian for talking about dark matter physics. You can have this A prime coupled to fermionic or scalar dark matter. But let's assume that A prime is light enough that it wants to only decay into standard model particles. Now this mixing will allow for production via neutron meson decays and in proton bremsstrahlung. So pi naught or eta go to photon and dark photon, or this continuum process where two protons collide and go out but also spit off the dark photon. Those two decays, we can write down the branching fraction. It goes like whatever that meson's partial width into two photons is, times this epsilon squared with vector of 2, and some kinematical factor accounting for the dark photon's mass. Yeah?
So is there any particular reason not to consider the Dralian production of dark photon?
We could consider the Dralian production. However, to do so, you need to go up to masses for the dark photon of 2, 3 GeV. And in an environment like DUNE, your production's not big at that mass.
So what is the photon count for this 120 GeV photon EV?
What is what?
How many photons are there compared to your final?
How many photons? Oh,
Right.
just made in like in Primakov processes?
No, just standard photon.
I mean, coming from ion decays.
No, they're not pi.
Oh.
Because the protons would be brainstorming. So there
I
are
would
lots of
assume
photons.
it's
Because
a
those
ton.
photons can give you these dark photons.
How?
A photon getting converted into dark photons. There are couple.
But don't you need a medium for that to happen?
Just any production process which produces the photon, you
Yeah.
change the coupling to dark.
That's effectively
Fine.
this
So you would
process.
just a simple brainstorming also then.
Yeah.
You're doing two protons. You don't need two protons. Proton getting stopped and the photon.
But if it stops, then you're going to have low energy isotropic ones.
Also high energy. That's 120 GeV.
Okay. So if we put all of these pieces together and we ask what is our flux at
Right.
the near detector, this
So
is
that's the net photon flux. That's the net photon flux. Like if you combine all those photons, is that the net photon?
I don't know about those ones, but this includes the virtual one, yeah. So we scale everything with this epsilon squared. So if epsilon squared is 1, this is what we produce. If it's lower, then this scales with epsilon squared. This is the pion contribution. You can't have A primes heavier than the pion mass in this way. Likewise with the etas. This difference between pi naughts and etas is just because you make many more pions than etas in the target. And then here's the proton branch-filling piece. You see this spike at about 800 MeV, and that's because at that mass, the A prime can mix with the standard model rho and omega mesons to give you an enhancement in this process. But ballpark, in less than 100 MeV, you're getting 10 to the 20 times epsilon squared dark photons in the direction of the near detector. This is assuming 10 years. So what happens to these A primes? They decay into standard model particles, like we said. So if it's light enough, all it can decay into is electron-positron pairs. So its branching fraction is all that, less than about 100 MeV. Once you get above 2 mu, then the channel A prime goes to mu, turns on. And then once other hadronic final states become accessible, those start to turn on as well. So they start to dominate at 700 MeV or so. For the masses that we are sensitive to, we can consider hadrons being mostly pi-pi pairs. So let's talk about backgrounds for such research. If we're looking for decays into electron-positron pairs, what could fate an electron-positron pair? Many people will think that in a liquid argon environment, your biggest problem will be photons, because photons will pair convert into electron-positrons. That will look exactly like your signal. But the nice feature of using the gaseous argon instead of the liquid argon is that the conversion length of a photon is much longer in this low-density environment. So, for example, if you have a pi naught decaying to 2 photons, in a liquid, those will convert in centimeters. But in the gas, the conversion length is order meters, and only 12% of photons will convert in the gas. The rest will reach the electromagnetic calorimeter and be identified as photons. So if they convert in the gas, which is again a small fraction of them, they can fake electron-positron pairs. But if you have a pi naught that goes to 1 photon that reaches the ecal and 1 that converts, well then you can tag that as a pi naught. So the only way that this background can be faked is if you have this pi naught, 1 photon converts in the gas, and the other one is missed. It goes in some direction that there's a crack in the ecal, or it's too low energy to be properly reconstructed in there. But there's even further reduction in this background, that the 1 photon that converted has to be in the correct direction. Because if this pi naught's coming out isotropically from the nuclear scattering, that photon can be in nearly any direction. But all of our signal will be coming from the target. You'll have a dark photon come in and decay into a pair of electron-positron with its vertex in the direction of the beam. So we think that there should be order 1 event from this type of background in the type of exposure that we're looking. Now, if you're looking for a dark photon decaying to muon, mu plus mu minus, or pi plus pi minus pairs, there will be bigger background contributions to this because there are muon charged current single pion events. So neutrino comes in and scatters, creates a mu minus, and sometimes it'll create a pi plus as well. Now, in the liquid argon, you might have some hope at distinguishing between these two, based on how much energy they deposit as they travel, but that's harder to do in the gas. Now, there's still some hope to use different kinematical cuts, like these directions I was talking about, or the track lengths of the muon and the pion. But the biggest hope is that they put a muon tagger in the detector. So there is work ongoing in the collaboration of looking into whether they can put enough space around the gas TPC, kind of interleaved with the electromagnetic calorimeter, to identify muons over pions. It's basically thick material to force the pions to interact and stop. So if they get a muon tagger, this should be a very low background channel as well. If not, it'll be a lot more difficult. So in terms of the dark photon mass, MA prime, between 1 MeV and 10 GeV, and the kinetic mixing squared, spanning 12 orders of magnitude, these are existing limits for such searches for dark photons. The bulk of them come from proton and electron beam dump experiments, E137, 141, or say NuCal. And then there's a limit on such dark photons from cooling of supernova 1987A. So you can ask, okay, where do we think DUNE will land in this parameter space? Well, these beam dump experiments were at closer distances to their respective targets than DUNE. So we can ask where in this parameter space is the proper lifetime of an A prime comparable to the distance to the near detector? And along this dashed line, the proper lifetime is about 100 meters. So we can ask, where do we see a bunch of events in DUNE? That is these two regions in red and blue. So the red region is the region in which at least 100 decays will happen in 10 years inside the gas detector. And comparably, the blue region is where 10 decays are expected in that amount of time. Now, depending on the mass, it will decay into different combinations of electrons, muons, pions, but 10 or 100 events in all of these regions of parameter space. So we expect that DUNE will be able to extend these existing limits a bit. Okay. Questions before I move on to a different model?
Just remind me, the left side of these beam dump experiments, this is not ruled out.
So, in principle, it is. We couldn't find any literature that extends these limits down below 2 MeV. And we think that's because as you approach 1 MeV, then the dark photon becomes long-lived. The branching, or the partial width into electron and positron pairs becomes small. So we think it's just a feature of that. In principle, we expect that this limit turns up like ours does and covers it as well.
So why does the shape
Why does it have this shape? Yeah, so that is because of this Bremsstrahlung production. This, you see that this lines up with that 800 MeV, where you're getting an enhancement to the production from mixing with the rho or rho mega resonance. So you just get a lot of flux there.
So here we just count the number of events.
Yeah, and we expect that this should be, close to the actual sensitivity if you included things like efficiencies. A similar model that you could look for is electrophilic gauge boson. So a vector boson that couples to an anomaly-free current of the standard model. LE minus L mu is one of those. Existing limits in gray and what we expect DUNE can do in color. It's not better than, but it's comparable to some existing experiments. Likewise, LE minus L tau, again, not as good as existing experiments. And the third, L mu minus L tau, now there aren't as many searches for this because it's only coupled to mu and tau. This dashed line is a cosmological analysis that constrains this region based on the number of effective degrees of freedom at the time of BBN. And we think that DUNE can expand it a little bit. There's a little green region in here that you can ask me about later if we have time. All right, let's move on to a different model, heavy neutral leptons. So you can make a bevy of assumptions about such heavy neutral leptons. We're going to make the least number of assumptions we can in order to do something interesting. So we're going to assume that it's an HNL, heavy neutral lepton, with mass Mn, and it couples to the standard model neutrinos in the standard model only via mixing with the charged lepton doublet. So via this LHN operator. And to make things even simpler, we're going to assume that N mixes with only one flavor of lepton doublet at a time. So in terms of the mixing angles, either UEN squared, U mu n squared, or U tau n squared is non-zero, and none of the others. Now, if you hope that such an N is responsible for light neutrino masses, this is too simple of a picture. But in principle, you could do a more complicated analysis of all of these independently. It's just a larger parameter space, and you start to lose insight as to where your sensitivity is driving from. So we think that doing this simplified approach is good to see where the power comes from. So how you produce it, it's similar to what I talked about for dark photons, where you're coming from meson decays. And even a better analogy is it's produced in the same way that the standard model neutrinos are produced in the beam. So let's look at mixing with the muon. There are 7 different production channels that we consider. Charged pion decay to a mu and an n, charged kaon decay, or a 3-body kaon decay. And then D meson decay is D and D sub s. One of these should be a D sub s. No, it's good. D's and D sub s decays. Now, especially these 2-body decays are exactly what DUNE is using to make the standard model neutrinos. Instead of n, this would be a new mu. Pi goes to mu, mu. But the interesting feature about doing so with a heavy neutral lepton is that in the standard model, the 2-body decays of mesons into charged leptons and neutrinos are helicity suppressed. That's why pions decay to mu's and new mu's much more often than it decays to electrons and new e's. But if n is heavy, if n's mass, let's focus on the kaon decay, if n's mass is comparable to the muon mass, then it can alleviate that helicity suppression and actually give you a helicity enhancement in producing this relative to what you would naively expect. So this is what our flux looks like at the ear detector of these ends, either in anti-neutrino mode or in neutrino mode for 5 years of each. This is assuming muon coupled HNL. The red lines in these panels are coming from charged pions. Blue lines are coming from charged kaons. And green and orange are coming from D and D sub s mesons. And likewise in here. Now, you'll notice, if you have a keen eye, that there are different tones of blue and red and green. The darker of those are positively charged mesons decaying. The lighter are negatively charged mesons decaying. So you'll notice in, let's take anti-neutrino mode as an example, the faint red line is a factor of a couple on top of the dark red line, meaning that you're getting mostly the decay products of pi minuses over pi pluses. And that's because of this focusing. Kaons is not so separated, but you see the D's down here. Now for the D mesons, they decay too promptly to be focused. So you don't get any separation other than what you get out of Vidya, for example. Now, if you look closely, you'll also notice these upturns near the thresholds, where the N mass is getting heavier than the muon mass. This is where that helicity suppression is being lifted, and you're getting enhancement to the production as a function of the mass. But no such enhancement exists in these 3-body decays. Sorry, I didn't clarify. The dashed lines are those 3-body meson decays. So you see helicity enhancement in the 2-body decays when the N is heavier than the charged lepton it's being produced with. It's easier to see that enhancement if you say that N couples to electrons than muons. So instead of being flat for the bulk of M, these are rising with N because of this helicity enhancement. So again, same color scheme, but now you see that as you let N be heavier, it's the one lifting the helicity suppression relative to the electron mass. Now, how does N decay? Since we made this simple assumption about it mixing with only one lepton, then its decays into standard model particles are well prescribed. If you added other new physics associated with this heavy neutrino, things would get a little more complicated. You'd have, say, a Z prime that makes it prefer to decay into a certain channel than others. But starting with this bare assumption, we know its decay widths into these channels and its branching fractions in these channels. In these plots, these are the branching fraction of N into different channels as a function of its mass, assuming it couples to electrons, muons, or taus. There are gray lines in each of these that are near the top that are under the category of irrelevant decays, and that is irrelevant for the sake of a search at DUNE. They are situations where there's only neutrinos in your final state, like N goes to 3 neutrinos. Sorry, we're not going to be able to detect that. and also situations where it decays to a neutrino and some other neutral particle. N goes to a neutrino and a pi naught, or another meson. We think that those final states will be background dominated, even in the gas detector. But we have all these channels. We can ask, okay, if you're a mu-coupled HNL with 200 MeV mass, what will it decay into most? It looks like it'll decay into a muon and a pion, or sorry, 300 MeV. It'll decay to a muon and a pion preferentially. So we can use this machinery and the flux to ask how many events of different types will we see in 10 years. So this is the existing limits on an electron-coupled heavy neutrino as a function of the mass between 1 MeV and 10 GeV, and in this mixing squared between 1 and 10 to the minus 12. There's a wide array of different searches for these types of things. Direct searches for pi goes to E plus some missing mass. Similar here with kaons. T2K did an analysis that's kind of similar to what we're talking about. And then heavier production in CHARM and Delphi. So where will DUNE land? With different channels, we think it will be able to set these colored limits by searching for N goes to a neutrino and an electron-positron pair, or a neutrino and an E NMU, or going directly to an electron and pion, or an electron and a rho meson. I'll highlight two regions, improving on this T2K PS191 limit by about an order of magnitude in this hundreds to 300s MeV range. And then this whole region here and above is all driven by D meson production. There's above here, you can't have K go to the heavy neutrino. And here we'll be able to improve on existing limits by about 2 orders of magnitude. Likewise, we can look at mu-coupled HNL. Again, existing limits are shown in gray, and this is what we think DUNE can do. Again, it can improve in this high mass regime by an order of magnitude or so. And my personal interest is this channel. N goes to nu E plus E minus, and it will be able to cover orders of magnitude in parameter space, vertically and horizontally. And it'll be able to improve on this by searching for electron-positron pairs. And tau-coupled HNL, there aren't as many existing limits in this, not surprisingly. And this is where we think DUNE will be able to land. It has this interesting shape where we can't rule out this gap because for these values of the mass in the mixing, it decays too promptly. It will decay between its production point and the ear detector. But we think we can exclude a decent amount of parameter space here. Okay? So is there more we can do with HNL? Let's assume that DUNE turns on and it measures, it finds this HNL, and they pop the champagne, they win the Nobel Prize, everyone's happy. But is there more they can do? And what I'll find is that it's improving on existing limits by orders of magnitude. Now these sensitivity reaches are where we expect to see about 10 signal events. But let's say that nature chooses this point in parameter space. Well, that says that DUNE will turn on and see 100 events. Is there something we can do with that data set beyond just saying that we found something new and interesting? And the thing that I think is most enticing is trying to determine whether such a neutrino is Dirac or Majorana in nature. So everything I showed you without telling you explicitly assumed that N is a Dirac fermion. Or more specifically, that lepton number is conserved. So if I make an N associated with a positively charged meson, when it decays, it will decay to a negatively charged lepton all of the time. Lepton number is conserved in this chain. However, if N is Majorana, it will violate lepton number in its decays a lot. So if it's produced associated with a positively charged meson, it will decay to both mu minus pi plus and mu plus pi minus with equal probability. So here's where the fun comes in with the ear detector. The gas TPC is magnetized. So let's say we have 100 N decays in this channel. Can we measure that it only goes to mu minus pi plus and not the other? But there's a difficulty. The beam isn't pure. You don't get just your K pluses pointing in the beam direction and no K minuses. There is contamination. So can we still measure it despite this contamination? So the question then is, how pure is our beam? So in these plots, I showed you that there's the dark and the light colors corresponding to positive and negative charge meson production. For instance, here, pi plus versus pi minus production is about an order of magnitude apart. So this beam would be very pure if N had this mass, whereas here they're closer together. So we can ask, as a function of the mass, how often do I get a N with lepton number +1 versus an N with lepton number -1 in my beam? So if you're being produced from pion decays, then the ratio is pretty good. You get lots of N's with lepton number 1 over -1, about a factor of 8. If you're in this branch that's coming from CAM production, it's about a factor of 2 or 3. And then here's where D meson production is in charge, and it's a factor of 2 or 3 in the opposite direction. Now the blue lines are if you're operating in neutrino mode. The red is if you're operating in anti-neutrino mode. You tend to want lepton number -1 in anti-neutrino mode. So for instance, 200 MeV, 300 MeV, this ratio is 2 or 3 in neutrino mode. So that means that for every 2 or 3 decays of one type, you see one of the other. How many events do you actually need to say something statistically about whether or not lepton number is conserved? So let's take this 250 MeV mass. The expected ratio, if their drag is about 3. Let's assume they're Majorana so that they decay into equally into the opposite charges. And let's ask how well you can measure that ratio with a certain number of events. So as you vary the mixing squared, you get more events. Up here is the number of events that you see. This vertical line corresponds to 20 signal events. And just using Poissonian statistics, you can ask how confident are you at measuring this ratio of that sample. So at 20 events, 3 sigma, you measure that ratio to be between about 2.5, 0.5 to 2. And you can rule out this expected drag ratio of 3 at 99% confidence level. This is if you can identify every decay perfectly, and if you know the mass of the N. We can generalize this and try to vary the mass and see where we can do this discovery. So let's look at this electron coupled channel again. This was the existing limits and what we think DUNE can do. And let's zoom in on this blue box. These are the existing limits now in pretty beautiful color. This is what we said that we think DUNE can do in terms of expected sensitivity. Again, there's an order of magnitude or so between these. And now we can ask, okay, if we assume some true value of the mass and some true value of the mixing, for what combination of those things can we rule out the Dirac hypothesis at 3 sigma? And that's what these black lines indicate. Now there are 2 lines for this parameter that we call A, of either 0.75, 75%, or 100%. That has to do with how often you correctly identify this E pi pair with the correct charge. It should be closer to 1 in this channel because electrons and pions look very different, and you can measure the charge in this environment very well. 50%, A of a half will be pure guessing, so you can't get that bad. And we see that even if A is only 75%, there's a good chunk of parameter space where if this thing existed, we could pin down its nature via these decays. And if we have perfect identification of the final state, an even broader region of parameter space for which we can do this. We can do the same thing with the mu pi final state. Again, this is the existing limits if it's coupled to the mu. And this is where we think DUNE can set a limit if it's going to n goes to mu pi. And we do the same analysis here where A of 75% or 100%, again, we think we can do something interesting for a wide region. I've got 10 minutes, let's do this. I'm going to shift gears completely. Any questions about decay things before I talk about scattering? So let's go back to DUNE Prism, and let's shift gears on the model to light dark matter. This is based on a paper from March with Valentina and Pedro. The model that we're going to look at here is very similar to the dark photon that I talked about a while ago. So the same terms to start. Dark photon called A prime with some mass, and then it talks to dark matter chi that is either fermionic or scalar. That chi has mass as well. Now the motivation for this is that maybe this is the dark matter chi, and it interacts with the standard model via this dark photon. Now, how will you make it? It will be very similar to how we made the A primes in the previous analysis, via neutral meson decays. M goes to a photon and a dark photon, or via this three-body decay goes to a photon and two dark matter particles, if this is preferential kinematically. So where in parameter space are we going to look? This is the A prime mass versus the dark matter mass. If you are below this triangle, where MA prime is equal to 2 times the dark matter mass, and to the left of this dashed line, then you will be able to produce a meson to a photon and a dark photon on shell, and that dark photon will be able to decay to 2 dark matter particles on shell. So the production rate will be high in this lower half triangle. Up here, the dark matter is too heavy to be produced via A prime to chi-chi bar pairs directly. And so if you want to have that happen via meson decays, it will have to be off-shell. Meson goes to a photon and an off-shell dark photon, which decays into dark matter pairs. Above here, the A prime is too heavy to be produced in the meson decay itself. So it will have to be off-shell again. So outside of this lower triangle, we expect production to be suppressed. Here we expect it to be very large. Now what do we do with this dark matter? Again, we keep track of the flux that goes in the direction of the ear detector. Here we're going to use the liquid argon instead of the gas because we are interested in scattering, namely scattering off electrons. Because it's a scattering process, signal to background ratio should be comparable in the liquid to what it is in the gas. So let's go where these things are higher in the liquid. What we should see is an elastic scattering of dark matter off an electron. That electron should come out pretty high energy and pretty forward going. Now there will be irreducible background from the neutrino beam of neutrino electron scattering, again, elastic, very forward going, or charged current scattering where you produce an electron and something else, some other hadronic activity, where maybe that hadronic activity is not identified by the detector. Here's where prism comes in. Because we said that prism can allow the detector to move off axis 20, 30 meters, the neutrino beam that is producing our backgrounds is peaked in the forward going direction. It's focused, so it's peaked in the forward going direction. And as you go off axis, not only is the flux lower, but it's also lower energy. And since the cross-section grows with energy, this means that your event rate will drop drastically as you go off axis. In contrast, our signal is coming from neutral meson decays. And those are not focused, so we expect our signal flux to be wide. We expect that it will die off less sharply than the neutrino flux. So here I'm showing, let's just focus on the solid lines, the neutrino-related background as a function of how far off axis your detector is, from 0 to 36 meters, in neutrino mode and anti-neutrino mode. The blue line is this charge current quasi-elastic scattering background, and the green line is the irreducible neutrino electron scattering background. Now I won't get into it in the interest of time, but we think we can veto this blue background. We think that this green background is pretty much irreducible. But now let's look at this green line. You see that there's also a dashed green line that is the signal plus background for a combination of parameters of interest. And you see that in the first bin, when we're on axis, the signal plus background and the background are nearly on top of each other. But as you go off axis, this gap starts to open up. And this is exactly what I was saying, where we expect the background to die pretty sharp, but the signal not to die nearly as much. And so what we propose to do, because this is a background heavy search with large systematic uncertainties with the flux, What we effectively propose to do is to measure the on-axis flux precisely, and then measure the off-axis flux, and see deviations from this slope because of the signal. So this is exactly what we think we can do with fermionic dark matter with 7 years of DUNE. If you just do this on-axis counting experiment where you're limited by systematic uncertainties, you'll get this dashed line for sensitivity. Over here you see that it's near the, or it's just barely better than existing limits from LSND and the mini moon dark matter run. But you see that if you do this off-axis measurement, you're able to get down your systematic uncertainties and get this solid line that's an order of magnitude or so better. And same over here. Now, if the dark matter is fermionic, there are stringent constraints from the Planck satellite that effectively kill off this entire part of parameter space already. And over here, all of this. There is a target that you want to reach, that this is this relic density target, where it could make up all of the dark matter. Planck already rules that out if it's fermionic. However, our limits look nearly identical to this if we assume that the dark matter is a scalar particle instead. And in that case, the relic density target moves up, and the Planck limit goes away, actually. Pardon? Or pseudo-Dirac, yes. We just looked at fermionic and scalar. But the point is that fermionic is not the be-all, end-all. So what we did is that we looked at this in a different combination of parameter space. And this is that MA prime versus M chi that I looked at earlier for fermionic dark matter or for scalar dark matter. And we see that there's a lot of parameter space for which we reach these interesting theoretical targets. So in the fermionic case, for all of these combinations of masses, we can reach that Planck limit. We can start to close that window with the Planck satellite. And for a subset of that space, we can hit that relic target, although it's not as interesting in the fermionic case. Above this line, as promised, the production isn't as high, so it's harder to set meaningful constraints. And it's also harder to interpret those in a dark matter freeze out like we can in the lower half triangle. For scalar dark matter, we hit that relic target for a very large amount of parameter space. So we can start to rule out well-motivated regions of parameter space if it's a scalar dark matter. All right, I will conclude here. I'll just tell you that just beyond using DUNE as a neutrino oscillation experiment, there's a lot of interesting pieces of its near detector that can be used for beyond the standard model physics. Specifically, the multi-purpose gaseous detector is great for looking for particle decays, and PRISM, because of its use for reducing systematic uncertainties, can also be leveraged for searching for dark matter. Thank you. Kevin, any questions?
So for background estimation for dark blue and dark matter surfaces, what if you turn off the beam focus?
Pardon?
What if
Turn
you
it off?
turn off the beam focus? I guess then you can significantly reduce the neutrino use to background.
Yeah, we didn't look at that. And the reason we didn't look at that is because our approach in these searches was not to say, how do we make the best detector to search for this model? We wanted to say, DUNE is going to happen. What can we get without having to spend an extra dime on the operation? Now, if you turn off the focusing, then you're trading something related to the oscillation physics to get something better for BSM searches. What we wanted to ask was, how do we do this without having to detract from the oscillations going on?
So basically you're assuming that, okay, so the beam focusing should be turned on constantly.
Because it's the priority.
Yeah.
Now, yeah, let's say DUNE runs for 10 years, it measures delta CP, it measures the mass hierarchy, and everyone's happy. Then maybe they could say, okay, let's turn off the focusing, let's do a beam dump run, which is what mini boom did, in a sense. Then yes, we expect that these kinds of things would get better. But the reason that we took the approach we did was because we wanted something that's completely parasitic.
But doesn't the PRISM affect the
No, it doesn't, because it allows them to reduce the systematic uncertainties in a way that it doesn't sacrifice any of their oscillation measurements. It actually helps their oscillation measurements. And that's because the flux at the near detector is so high that they will be quickly systematics limited. And so they can trade off some of that limitation by going off axis, basically dividing up their statistics between on and off axis to try to beat down those systematics. Yeah. And they'll have plenty of events. They'll have more events than they know what to do with.
So detector, you said you didn't talk about it, but how do you get your charge current equations at elastic background?
No, I'm going forward. Here we go.
No, actually,
This is the background.
that's the background.
Yeah, here. So you're asking about.
Yeah,
That's-
like you said, forget about that blue thing, but.
Yeah, so you see that the count rate of these backgrounds is about an order of magnitude or so larger than the neutrino electron scattering, or even more. So how we propose to reduce that is using this kinematical relationship when it's truly elastic scattering, something hitting an electron, the same thing's going out. The outgoing electron energy and its angle, E theta squared, must be less than 2 times the mass of the electron. Just kinematics tells you that. So the neutrino electron scattering background in this quantity has this green shape and this harsh cutoff. And our signal has a similar but different shape and again a harsh cutoff. Whereas the charge current background, you can have wide angle scattering because it's off a nucleus. Now, I'll note that this blue distribution, the binning between these is inconsistent. And so in terms of how much contamination there is down here, this should be shifted by 2 orders of magnitude in your mind based on the binning. So if you can make a cut on E theta squared, even if it's not 2 ME but 20 ME, you will be dominated by the intrinsic background. Any other questions?
Just out of curiosity, so what would be the strength of magnetic field in the gas phase?
You're in the liquid part, you mean, or?
The gas part.
So I think the biggest is this kind of Dirac versus Majorana separation that I talked about.
Right.
If you can tell a mu plus from a mu minus and a pi plus from a pi minus, then you can start to do these interesting things.
Yeah.
Oh, the value of it.
Yeah, value.
Oh, it's a half Tesla.
Half Tesla.
Yeah. Sorry, I think you meant strengths in terms of an analysis. Any other questions? Fine, let's not get it one more time. It's commensalistic. I've had this debate with people. Oh, really? Commensalistic means that you get both, or one creature benefits and the other not.
Okay.
So you can benefit.
But you're adding to this program.
Thinking about
Well, it's a question of which proton.
photon.
Well, you're adding to the scientific program, which puts the
Also
cost
produce
in
a
those values.
It's like Compton scattering, but instead of a gamma E, it's gamma E, that's a prime E, right?
So actually the reason why I'm
This
But
one,
the-
gamma E to prime
Yeah.
E, right? So I was just thinking about, one of the ways we're thinking about
There are lots of-
axions this way, right? But you can also do prime.
So that's.
Always anything with this, right? Yeah, what I was thinking about though is and then of course on the germanium side, since they have such good electrons.
You have more
Anyway,
photons which are around.
you can see the scattering that way.
I am a little worried.
So I was just wondering what the,
Protons are going to find sources of photons.
Okay.
This is neutron.
there's a search for A primes that can be done with these
A lot of
These are kind of octacated.
And this one, here, this one is the only thing, there is a 1G.
Yeah.
So that's why all the activities are.
Yeah.
Yeah. But for you, it's a one section, but. So this is like.
But we want the high energy one.
Yeah, so
because
the
they'll have
photon
a
can also
longer
just
lab
decay
rate.
in the detector.
Okay.
You can produce A prime.
So the low energy
have
ones
it
won't
decay,
contribute to our
or it can
signal.
scatter.
That's true. But the question is 120G, what's the point? This is 1G.
No, well, production is just from
Photon
gammas
spectrum from
to A prime.
1G.
Okay.
So that's the thing I was looking.
But the A prime should be.
Interesting.
And see, so much of
It doesn't have to decay into two photons to E plus E minus. It can scatter
And
in the detector,
And
right?
when
It
we
can do
include
Compton
this,
scattering as
we
well.
kind of, we see that.
If it lives long enough
for
in the
this
detector,
region, we
it
understand
can then
the
scatter.
dark matter.
Cool.
And also, for
A prime E to
coherent dark
gamma E.
matter is quite good.
Yeah.
Like, we saw that it's better than.
Right? It's like light shining through
I have a fight to pick about that because I heard this came up
a reactor wall.
at the Magnificent Seven.
Gamma comes in, produces,
Valentino
it's just like the
told me
axion
this
case.
came up, so
So
I made a
looking,
slide.
looking for axion electron. We have axions
So it's zeroized
produced
figure, right?
from
Yeah, yeah.
Compton,
But if I'm
and then
not
axions
mistaken,
are detected.
What you're assuming here is
Same
the
thing,
fixed
A
dark
prime.
photon mass for production, and then a different mediator mass for the scatter.
Ah,
Well, surely there are other bounds, but I don't
So,
know how tight they are.
So if the opposite of the answer,
in fact,
Of course.
if it's, if the
I don't know,
mediator
but
mass
it's not
is
frustrating.
less than the dark photon mass, they're same.
Okay.
If it's larger, then we kind of change that.
Yeah, definitely.
But also in the paper, we showed that case where dark photon and mediator mass, they're same.
Well, so let's look at this and try to compare if they're the same.
Like,
So this was 75 MeV, right?
Yeah.
So if they're the same, then your limit with current or with
Right.
20 ton years of argon is.
For 20 don't believe it because we scale the background, so they're.
Okay, so let's take the current then.
Right.
That says that it's
Right.
epsilon squared 10 to the minus 7.
Right.
But if we look at the same mass, because all we assumed is the same mass in these cases, if we look at 75 MeV here, we're able to get to, 4 or 5 times 10 to the minus 9.
Okay, so, and ours is, you are saying 10 to the
10 to the
minus
7.
Okay, so you were saying that for the existing CSI, what we have, that's the existing CSI, so you are.
Or even the future liquid
For
argon.
future liquid argon, what happened, we just scaled the backgrounds. So scale the background, so you don't.
But you, that was, 10 to the minus, about 10 to the minus 8.
Actually, now, so what happened? So this is an interesting thing you said. So what we did, we scaled all the background for CSI to liquid argon. But now, what Coherent has a paper, recent paper, and what they have done there, they said that they can reduce some of those irreducible backgrounds which are happening for CSI to much lower level. So it's a much better.
Should be better.
Oh, yeah, much better. So here is the most conservative. So if you look at that plot, you may not want to build a 20-ton argon,
Yeah.
right? So, but what they have done, they have cut the background.
Okay.
So it's much better.
Cool.
In fact, what the Coherent, their projection with a 610 kilogram for 3 years is much better than any top scale argon.
Cool.
Yeah, so here we did 75, but it does not matter up to
As long as the.
120. and
Yeah, well, so that's why I saw this plot and I got very confused.
So maybe you can compare these.
Okay, let's take 100 MeV.
Yeah, 100.
And that's about 10 to the minus 7.
So yours is
100, yeah, we're at 10. Cool.
So it's because but now with this additional photon, ions are kind of leading the charge, but it can go beyond. Oh, another thing, sorry. That pi minus, the story in that plot is pi minus.
But pi minus capture.
Yeah, but then we realized we need to add pi naught.
Okay.
And once you add pi naught, you can break that 130. And if that, even though that, because pi naught is very risky.
So
But you still can't.
Energy.
It's energetic, but you can't get a mass heavier than 130 MeV.
But it can have, it's true, so how it's happening at that time?
Unless you allow it to go off shell.
Yeah, right, you can go
Okay.
to offset, that's the point.
But I think weren't these plots assuming that the ratio between the dark photon and the dark matter mass was 3?
Yeah,
So then,
so that means,
what's gonna happen is you're gonna go off shell and this is gonna get a lot weaker.
We could.
Yeah, okay.
But with the photon though, it can be that constant because now with the you have photons with a larger energy.
Okay.
And that can be that dark photon. Yeah, that plot we have not done. Actually,
Okay.
we are in the process.
Cool.
of making it. And I think for your case also it will change.
Probably, yeah.
If you include all the photons, collect all the photons, I think things will be much better.
Cool.
And so how many protons are there, protons are target for you? Like how many? What's the
21
number?
per year.
10 to the 21. So same as COVID.
I think it's less. Yeah, I thought it was like
Thanks
just
for
like
23.
23. 10 to
2
20.
times 10 to the 23. 10 to the DUNE is 2 times 10 to the 21. For 5 years.
Okay. So 10 to the 23. Okay. So then I think no matter what then, oh, so your plot is for how many years?
we did 7.
Ah, so that's why you were better.
Yeah. Well, but the POT still isn't bigger, but.
No, no,
bigger
the bigger, but also in terms of reach is big.
Oh, sure.
So, but over there, like for our plot, it's 308 days, 308 kilogram.
Okay.
Okay, I see. So I was wondering, like,
There's so many different factors.
Yeah, yeah, so
going
many.
between them, yeah.
Yeah, so we now have to change that plot, but we put an update. And then we'll add all the photons and then, and because the adding all the photons, what will happen, this side wouldn't be that flat.
Yeah. Because that makes sense. Interesting. Look forward to seeing it.
Yeah, and for your background also, I think one can do better, right? Like if we do the window.
Probably, yeah, because, yeah, and measuring the electron energy would also help.
I think at the end, DUNE probably would be better because it's so much huge. Yeah, but now there is a new experiment at Los Alamos called CCN.
Oh, coherent capture films.
Coherent capture. They are running a 10-ton
Okay.
fiducial 7-ton.
Cool.
Yeah, so it's a, but their proton beam is little less, 8 GB, 800 MB.
800 million
No,
kelvin.
no,
Yeah.
these
Okay.
experiments.
So it's all photons.
Yeah, all photons.
So it's a lot of photons.
It's a lot of photons. And detector mass is huge, so, yeah, we also make a projection of them, so they look better. But I don't know their background, so it's.
Yeah. So a lot of neutrons coming out.
Yeah, a lot of neutrons, but they're doing lots of shielding, so I don't know. Yeah, that's a problem.
Interesting.
So, but for you, the neutron is not a problem, the proton is.
No, no, because you're so far downstream
So far
that
down,
if a neutron or a proton made it through to 300 feet, or 300 meters of Earth, we'd have a problem.
Also, it's interesting, like for you, if you are doing it hadronic and leptonic detection. But for coherent, it's hadronic
Yeah.
already.
Well, we just want the electron back. The electron that matters more for us.
Yeah. But for coherent, it's all like Q. So there is a complementary.
Yeah. So once coherent detects it, once it finds it,
Mhm.
DUNE can turn on and measure it.
Yeah, yeah. And coherent has a new set of data, but we don't know, like, they are going to publish it soon. So
Cool. I was thinking that it was already out because I saw several
No, no.
coherent pheno papers recently.
Oh, these are based on the fact that, remember one where we came up with that Wenchi
Oh,
analysis?
okay, so there
So
were-
people started putting that Wenchi.
Okay.
And so that,
But now that there's more data.
more data, yeah, I think so.
Neat.
And, we kind of avoided the quenching here because what we did, we looked for the long
Did you hear about this workshop? I think it was early November. And it was all about, it was over a weekend at Fermilab, and it was all about using timing for physics in neutrino beams.
Early November, actually that's the time when magnificence.
I think it was the week before that.
Oh.
There was a wine and cheese at Fermilab from Matt Wetstein, who is at Iowa State, and they're working on this idea of if you could make the proton beam for DUNE bunch finer, like nanosecond level, and you had a detector that could read out events nanosecond or picosecond level. The neutrino flux is different shortly after the bunch hits versus slightly later, because the pions that are highly boosted will live longer and then decay to neutrinos versus the low energy ones will decay quickly. And so if you had timing, you have another handle on the neutrino flux. And I know that you guys are interested in that coherent, and that's something you can use with dark matter searches and DUNE too, yeah. But I wasn't able to go to the weekend talks, but
Yeah,
people are
because
thinking
you
about
can
this.
clean up the background.
Exactly.
You can clean up the neutrino background.
Yeah.
So that's what we did with Code.
Yeah.
Here also you can do the same thing.
Wouldn't that be amazing?
Yeah, that's perfect. And once you clean up the neutrino background signal, just
Oh,
because
yeah. I mean,
before this dark matter constraint was proved.
I mean, if we look at our, where we're driving sensitivity here, so this was a value that's, we're sensitive to. There's tens of thousands of background values.
Yeah,
Could you imagine if you could get 4 orders of magnitude lower? That'd be
No,
amazing.
actually during the coherent analysis time, we realized that if we had that neutrino background, they are not sensitive to dark matter at all because it's on the top.
Exactly.
Once you clean it up, then it's so much better.
If we just had the on-axis measurement, we're not sensitive. Neat.
No, I think people are becoming more creative with all these experiments. This is much better.
More fun for us.
More fun for us.
Okay. Cool. Make sure I'm
Very
not
nice.
going as high thoughts. And that paper about decays should be out hopefully next week.
Oh, perfect, perfect. And check the photon production because
Yeah.
that would be my own concern for because of course you are under